find the electric field outside the sphere at a distance r is greater than the actual radius of the sphere from the center. So, you can do this by doing Gauss's law, and so your Gaussian surface would be a sphere outside the sphere that you have. And so using Gauss's law, which is integral of E dot dA is equal to Q enclosed over epsilon naught. Alright, so for this problem, the answer is actually really simple. The Q enclosed is, you have to take the whole charge inside the sphere. So the whole charge inside the sphere is positive Q plus negative Q. Positive Q plus negative Q, since they go to the same magnitude, different directions, is equal 0. So Q enclosed equals 0. So once you put 0 in there, then the whole answer turns into 0 because you're multiplying everything by 0. So your answer for part A is 0. Okay, so part B asks you to find the electric potential V outside the sphere at a distance little as greater than big R from this center. Okay, so we can figure out voltage by using V is equal to negative, V is equal to negative E dot ds. In this problem, that we've already determined that anywhere outside the sphere, the electric field is going to be 0. And so V is thus equal to the integral of 0 dot ds, which is equal to 0. For this problem, we're going to use Gauss's law again, because it asks us to find the electric field inside the sphere at a distance little r is less than big R. So we're going to do integral of E dot dA is equal to Qn over epsilon naught. Alright, so for this problem, dA is parallel to E because as a sphere grows by radius, the electric field also grows by radius, and so they both increase by like the same proportion according to R. And so, according to that, we don't need the dot product anymore. You also don't need the integral outside the E, or you can take E outside of the integral because E is constant according to this certain Gaussian surface. Since it's a product of R, or since it's a result of R, if the R is not changing, then it's constant. So we're going to take the E out of the integral. Alright, so for Qn, there's 3 types of uniformly distributed charge. There's lambda, which is Qn over linear charge. So that's just distance, or length. There's sigma, which is equal to Qn over area n. And there's rho, which is equal to Qn over volume n. For our purposes right now, since we are using a sphere, we're going to use rho because of the volume. So if we do go ahead and use rho, alright, so rho is equal to Qn over Vn, which is also equal to Q total over the volume total. So since you're solving for Qn to get this part of the Gauss's law, you're going to solve for Qn in this proportion. So Qn is equal to Q total times Vn over V total. Oops. And then, since inside the sphere, at any given point, a radius r that's smaller than big R, the only charge you have enclosed is this small little q. Because it's a conducting sphere, and as we've determined, there's no electric field inside the sphere coming from the outside sphere. So this is equal to q or positive q. And then the volume of a sphere is 4/3 pi. Since this is your enclosed volume, it's little r cubed. And over your total V, which is 4/3 pi big R cubed. So here the 4/3 and the pi's cancel out, leaving you with q little r cubed over big R cubed. Alright, so the total charge inside the sphere is actually going to be big Q minus this, because you already have the big Q given here. So your charge is going to be Q minus Q little r cubed over big R cubed. And so we're going to replace that for Qn. So E integral of dA is equal to Q minus Q r cubed over r cubed over epsilon naught. Alright, so for this, the area of the sphere, which would be the surface area, is going to be 4 pi r squared. So E is equal to Q minus Q r cubed over r cubed, and then times that by 1 over 4 pi little r squared epsilon naught. And this should be your answer. Okay, so this problem is asking you to find the electric potential inside the sphere at a distance little r is less than big R from the sphere. So for this problem we're going to use B is equal to the negative integral of E dot ds. So now for this problem we're going to be taking electric potential from infinity to r, or to little r. So we're going to be taking two, so that's going to give us two separate integrals. You're going to take integral of infinity to big R of E dot ds. And then since or add another negative from big R to little r. Okay. So this is going, since the electric field outside of the sphere, as we determined in part B, is 0, this is going to give us 0 minus, oops, forgot to add that in there, is going to be giving us 0 and then minus E dot ds from big R to little r. Find the electric field from big R to little r, which is, I think we've already found it. We found it in part B, and so in part B we got the answer. E is equal to 1 over 4 pi r squared epsilon naught times big Q minus Q little r cubed over big R cubed. And so from here this can be simplified into E is equal to Q over 4 pi epsilon naught, and then 1 over r squared minus little r squared over big R cubed, I think. Or no, just kidding, sorry. Little r over big R cubed. Alright, so for this, since you can use this in this equation, so you're going to take, so this is going to be Q, since this is all constant, over 4 pi epsilon naught, and then negative times e, or times the integral of e dot ds. And so your e, the only thing that's changing as a function is a little r. And so there's going to be 1 over r squared minus r over big R cubed. And then dr. So you can take this as 2 separate integrals. So I'm going to go on this side. And so, so from here you can go negative q over 4 pi epsilon naught times the integral from big R to little r of 1 over little r squared dr minus the integral from r to r, or big R to little r, of r over r cubed dr. And so as a result of this, you get negative q over 4 pi epsilon naught times, so the result of this integral is 1 over r if you solve it, or negative 1 over r, and the result of this integral is equal to negative r squared over 2r cubed. And that's evaluated from big R to little r. So from here we're going to evaluate this from big R to little r. So you're going to plug it into this part of the equation first. So this would be negative q over 4 pi epsilon naught of negative 1 over big R minus 1 over, or plus, since you're adding a negative, plus 1 over big R. And then minus r squared over 2r cubed, and then plus big R squared over 2r cubed. And so you can cancel this out and just get 1 over 2r, or 1 over 2 big R. And so you can simplify this even further. Once you do simplify, you get v is equal to q over 4 pi epsilon naught. We're going to multiply the negative inside here. So you get 1 over r plus r little r squared over 2 big R cubed, and then minus 3 over 2r. And this should be your final answer.